Just a second.
Yeah, I have started the recording. Can start in a
Okay. Okay. Should I start?
No, I'll introduce you first.
Okay,
Yeah.
cool.
Sorry. So, hello everyone. Today we have with us Guillem. Guillem is a PhD student at Dynamic Vision and Learning Group at TU Munich. Before that, he obtained his master's degree from TU Munich as well, and he was also working as a part-time research assistant at DVL. And he completed his bachelor's from University of Barcelona. His research interests are focused in the domain of deep learning, computer vision, and discrete optimization. Today, we are going to discuss his paper, Learning a Neural Solver for Multiple Object Tracking. We are glad to host you. Please continue.
Okay. Thanks a lot for your introduction, Shimbi. So yeah, I'm going to talk about our CVBR paper, which was actually my master thesis, which is about learning a neural solver for multiple object tracking. So yeah, I think there's no need to introduce myself since Shimbi already did that. Okay, so before we start, just a quick definition of the problem. The problem that we're trying to do here is the solve is multiple object tracking, and specifically we will focus on the tracking by detection paradigm. So what this means is that we have as input a sequence of RGB frames, and we are also given a set of object detections. So essentially, we apply a detector to every frame so that we have a set of boxes for every object, hopefully. And our task is to join these boxes into trajectories. So essentially to draw the trajectories out of these boxes across the video. Okay, so before we go on, we might ask ourselves, why is this problem important? So it's actually a pretty basic problem in computer vision, and it has several applications. So the first one, and maybe the first one that comes to mind is autonomous driving. So for instance, in autonomous driving, generally, we're not only interested in whether there's an object or not. So essentially, object detection is probably not enough. But we also need to know how objects are moving, because essentially we need to be able to predict their future locations. And for that, you first need to be able to track them in order to be able to plan trajectories. Okay, so the second one, and again, this is quite obvious, it's just surveillance. So for surveillance applications, you don't need to track objects across videos. And then this essentially, tracking can also be applied in biology. So for instance, for cell tracking to, I don't know, like detect anomalies in the movement of cells and things like that. This can be useful in biology. Okay, so this was a bit the general motivation of the problem of tracking. And now I'd like to move on and explain a bit of the background of multiple object tracking, and specifically graph-based tracking. Okay, so as I said before, our input here is going to be a sequence of RGB frames in a video. And for every frame, we apply a detector independently, and then we're going to get object detections. So essentially, what we have is a set of boxes across the video, across time. So the typical way that this problem, the problem of tracking, has been approached is by formulating it as a graph. And in this graph, every object detection, so every in this case, every pedestrian is a node. And what we have is edges connecting all nodes that are in different frames. And essentially, these edges, they represent the possibility that two nodes belong to the same trajectory. And the idea is that out of this representation, the goal is to determine which edges are actually connecting nodes that will be in the same trajectory. So in this case, for instance, we see how this edge here, I don't know if you can see my mouse here.
Yes, we can see it.
Okay, so you see, for instance, we have this graph formulation of this sequence. And we have, for instance, that we know that there's a trajectory here in blue. And essentially, this corresponds to having an edge between these two object detections. Same thing here for the yellow guy. We have these edges that kind of draw a path across the graph. And this path represents a trajectory. So in summary, the idea is that by seeing the problem as a graph partitioning problem, we can reduce tracking to identifying a subset of edges in the graph that will be representing these trajectories. Is this formulation clear?
So you are trying to check frames. Sorry, is there an echo? Sorry.
I hear you
So
correct.
you have the edge based on the frames. Is that
Based
correct?
on, based on what, sorry?
Are you having the edge, drawing the edge based on the object in different frames? That's it? That's about it? Okay.
Exactly, exactly. Essentially, two objects are in different frames, then you might have an edge among them, indicating that they might be connected.
Okay, thank you.
Sure. Okay. So, okay. Sorry, any question?
No. There seems to be some echo, but yeah, carry on.
Okay. Okay, so this is the high-level idea of the overall formulation of the problem. And now I'd like to move on to a more detailed view of how this works in practice. So essentially, the idea is, I said, like the idea is to represent the whole thing as a graph, and the end task is to partition this graph. But how exactly this is done? So the idea is that in general, this process is subdivided into two steps. So in the first step, the idea is that we want to do some feature extraction on the appearance of boxes and also get some spatiotemporal features. And the idea is that for every possible connection in the graph, so for every edge, we want to assign it a cost. And this cost of this edge represents how likely it is that two object detections belong to the same trajectory. So the idea is that, for instance, for edges that are connecting objects that are very similar and very close in time, this cost should be very low to encourage, essentially representing that it's very likely that they are together. And in contrast, for objects that are like very different in appearance, for instance, this cost should be very high, indicating that it's very unlikely that they are actually in the same trajectory. So assuming we have defined a cost for every edge in the graph, this I will explain later, but assuming we have defined the cost, the task then is to optimize, to run an optimization problem on these edges with these costs to actually partition the graph. So essentially, we should solve a combinatorial or discrete optimization algorithm on top of these costs to say, okay, out of this cost, which is the cheapest way to select edges based on these costs and actually partition the graph in this way. Okay, now this was a bit high level again. Now I'd like to explain each part separately in a bit more detail. So regarding the first part, feature extraction and the definition of these costs for every edge. So the typical way to approach this is to essentially consider every different pair of object detections in the graph. And then also considering, for instance, some spatiotemporal features like how far they are in time, what their spatial distance in space, and taking information like that, and feeding this to a neural network. So for instance, this could be a Siamese network where you could have a CNN on top of each different box and extract features while sharing weights. And essentially the idea is that there you want to predict a score, to predict this cost, representing whether these objects will be together or not. So in these cases, like in this case, for instance, it is very easy. Like we see clearly that from appearance alone, we can see that these objects will not be together. And the idea is that here, the network should output a very high cost. In some other occasions, for instance, we see that appearance can already tell us that this is most likely an edge connecting to objects in the same trajectory. So this should output a very low cost. And the idea is that we repeat this process for every pair of object detections until we feel the costs for every edge in the graph. Okay. And what happens here, if you think about it, is that based on a single pair of object detections, it can be very hard to know how high the cost should be. So we see, in this case, for instance, we see this object in which appearance is always the same across frames. So just based on appearance alone, it's very hard to tell which cost should be higher. So the edge connecting the first and the second frame, or the edge connecting the first and the third frame. So the idea here is that unless you get to compare different pairs, it's very hard to know which pair is better than which other pair. So the basic idea here is that just pairwise relationships might not be great. Ideally, we would like to have some sort of higher order relationships. So for instance, we would like to have comparing pairs, and for every pair output a single cost, or something of that nature that would somehow encode higher order information. So not only pairwise relationships, but also so something that accounts for like relationships of higher order. But this again brings us to the second part of the problem, which is that if we want to somehow encode higher order information in the graph, then when we feed this cost to an optimization problem, by having higher order information, what we end up is with a much higher, much more difficult problem to solve. So for instance, these comparisons among pairs that I was talking about, this would translate into a quadratic problem, which in general is NP hard. And this is actually very expensive to even approximate. So yeah, so the idea, I don't want to go into too much detail here on the optimization details, but the idea is that here we would have a cost. So this cost vector would have one component for every edge, and this y would determine which edges we select in the final graph. And essentially, yeah, would have some constraints which I haven't written here, but the idea is that this would be an optimization problem that would allow you to select which edges you want to keep in the graph. But yeah, if we want to have like more fancy costs, so to say, then we end up with a very hard optimization problem. Okay. This, I hope, made the background of the problem a bit clear.
Yes. Please go ahead. Yeah.
Okay. So then,
Yeah.
sure. Please.
One question. When we are talking about optimization, although for a very fancy high-end driving car, it would be tough, but if we are trying to mimic a robot, a delivery robot, which is traveling in a setting where human interaction is a lot, this thing is quite possible, right?
Mm-hmm. So you mean, I didn't understand the question. So you mean can you repeat it, please?
Yeah. So, I'm asking that since the whole optimization of the quadratic equation might be difficult considering a situation where we are talking about an autonomous car, but for a very miniature delivery robot kind of a situation, we can implement this proposal, right?
So yeah, so here I skipped some details. Like the thing is that quadratic programming in general, as you might find in robotics or some other fields, like these, there are efficient solvers for it. But the problem here is that this is not a quadratic program, but a quadratic integer program. So the thing is that quadratic integer programming in general is very hard. So if you don't have the integrality constraint, so if you are like working in a continuous space, this is fine. This you can solve efficiently. But the thing here is that since we're working with graphs, our decision variables are either 1 or 0. And this makes optimization very hard. Like even integer linear programming, so even if the cost is linear, this is already NP hard, but then for some specific formulations, you can solve it efficiently. But quadratic integer programming in general is very, very slow. But yes, I think that's
might be computationally expensive.
Exactly.
So which applications are more suited that you would consider for this graph-based object? Which applications do you think are appropriate here?
Exactly. So the thing is that anywhere you need tracking, in general, you always are going to be using a graph. Like there are really few exceptions. Like for like autonomous driving, for instance, you generally need to do online tracking. So like the thing is that now I've been talking about generally having like several frames, but this is probably not very suited for real-time applications, because in real-time applications you cannot like peek into the future, right? So you can only work with one future frame at a time. So this setting that I'm describing here wouldn't be exactly that. But the thing is that if you just think about what happens if we remove one frame here, we just have a graph with two frames, like essentially these two detections here and these three detections here. This is just a specific case of what I'm describing, and in this case, you could still apply the same logic. In this case, like this optimization problem would just be bipartite matching. So we would need to match objects in one frame into the other one. And this is actually the most common way to approach tracking for autonomous driving with this bipartite matching, which can be solved efficiently in that case.
Oh, but so for pre-recorded videos, this should be fine, right? For pre-recorded videos.
Exactly. So essentially, this is a very general formulation, and most tracking algorithms rely on a variation of this formulation. So either if it is for autonomous driving, then you would just probably use two frames, but still the idea is the same. If you want to do video analysis, then you probably will consider a longer sequence of frames. But again, you would probably end up with a graph formulation. At least until recently, all the state-of-the-art tracking methods for several domains were all graph-based in some way.
Got it. Thank you very much. Please carry on.
Okay, thank you. Okay, the message I wanted to get here is that in general, there's a trade-off. So if you want to get really good tracking results, you probably need to have some fancier costs, and essentially you end up with an expensive optimization problem. On the other hand, if you want to have something that's faster, that's suitable for real-time applications, maybe, then you cannot go too fancy on the optimization side. So the overall idea is that we somehow have a trade-off between how good tracking results are and how expensive the problem is to solve. Okay, this was all a bit general, but now let's look at some specific examples of related work and how these formulations are applied in practice. Okay, so one of the earliest works combining this graph. I mean, I'm not going to talk here about the original papers describing these graph formulations because they are a bit old. But I will jump directly to their combinations with deep learning. So like these graph formulations have been around for quite a few years. But one of the first papers that actually somehow combined these graph formulations with deep learning was this paper by my advisor, Leal-Taixé, in which they introduced a Siamese network that took into account optical flow also. So the idea is that for every pair of detections in the graph, they...
yesterday we had a talk by Professor J.V. Gemert, and he has done some work in optical flow. He's from TU Delft. And yesterday itself, we were discussing how optical flows can be computationally expensive when we are considering motion prediction. So that is why I asked you the question that can this be a solution to optical flow problem or not?
If these approaches could solve optical flow, like this graph formulation, you mean, or what?
No. Like the question I asked, that if this could be used for delivery robots, that was relevant to that. Like if this is not so computationally expensive, can it replace the optical flow mechanism, because that is very computational?
I see. I get it now. I see. To be honest, we would have to see, because as I was saying, if you want this to be fast, then you want to make sure that the way you define these costs, so this Siamese network needs to be very small, very cheap. So maybe not. I'm not sure. To be honest, I'm not super sure about this. I'm not very familiar with like these real-time applications.
But anyway, for robotics as well, Shambhavi, it is still real time, so this could not be used. So Right. So please go ahead.
So yeah, I mean, this one, for instance, here, as you said, you do need optical flow, which is not so cheap to compute. So this probably wouldn't be suited for that. And the idea is that here you would have, you would take every pair of detections with their optical flow, which somehow informs you about the relative motion of people. You would feed this to a CNN and then get a cost. And this was a bit old-fashioned here. I think no one would do this like this nowadays, but at the time what they did is that they took those Siamese CNN features they pre-trained them on their own, and then they combined it with some additional features of relative position and relative geometry. And then they feed this to a gradient boosting classifier to get a final matching prediction. So essentially, this is a classification problem. So for every pair of detections, do they belong together or not? And then they just input this cost to a linear programming solver and got the results, which at that time were state of the art by a significant margin.
Right.
Okay.
Thank you.
So now, moving on, one step forward towards this idea was that, as you see here, as I said before, we have, on the one hand, we have this Siamese network, this feature extraction, and on the other hand, we have the need of solving an optimization problem, right? And what this paper tried to do here was to somehow marry these two problems. So learning and optimization should somehow be combined. This was the main idea of this paper, and I think it did a nice step in that direction. And what they did is they found a way to somehow backpropagate. Okay, so the idea is you have your input images, you feed them through a CNN, and then you get your cost for every edge. And then you use these costs for an optimization problem solver. So what they found is a way to backpropagate gradients out of through the solver. So the idea is that they would compute a loss after the optimization problem was solved, and then they were able to compute gradients all the way through that optimization problem. So you could see somehow the optimization problem as a kind of layer of a bigger network. This was, I think, a good idea, theoretically appealing. But what happened though is that in practice, this didn't seem to work that well. So if you look at the actual numbers, this solver didn't seem to, like this backpropagation through the solver didn't really seem to make so much of a difference in terms of performance. Okay.
There is one box without any object. What is that? In the first image, in the top P0, we have two objects, and the third one.
Exactly. So this I didn't go into so much detail here, but in theory, I was talking always about costs for edges, but you could also have a cost for nodes. So for every object itself, you could have like a unary cost representing the likelihood that the object is an object or it's a false positive detection. So it's there's nothing there.
Okay.
So the idea is that in this way you can also not only link objects but also filter out false detections.
Okay.
With the optimization problem. Okay. Okay. Now I would like to also talk about this is more of a set of papers that all focus on, they are all graph based, but the thing is that they in general use a graph formulation called correlation clustering or multi-cut. And the idea is that these problems generally, these papers in generally, like here, for instance, they build the graph in which you have like several levels. So one level is here, is like the top level, which is based on bounding boxes. And then you also have these small low-level features, which you also try to join. And the idea is that you want to partition not only the boxes, but also these low-level features. And these methods, the thing is that if you think about it, like you have to define a cost for every low-level feature, also from low-level feature to boxes, also among boxes. And this all was done in a handcrafted manner. So essentially, they have to somehow define, okay, we take time distance has this relevance in the overall weight, spatial distance has this relevance. This was all handcrafted. And these methods, which were based on graph formulations of this sort, these were for some time these were like state-of-the-art performing. And I think that they are, again, theoretically appealing, but first of all, they are very slow. Like this could be less than 1 frame per second of speed, which for practical applications is definitely not great. And also the thing is that these kind of problems, they require a lot of handcrafting, as I said. So ideally, you don't want, as a user, you don't want to be defining all these features manually, but ideally, you would like to learn all of these. So despite this being like very strong performing methods, they suffered from a lack of scalability, you could say, and maybe not being that practical because of their slow speed.
So what is an example of a handcrafted feature, like an example?
Exactly. So an example. So for instance, um, like the idea is that let's say you want to define the cost between boxes, right? So you have to combine, first of all, how far they are in time. So this is one feature. Then you have to combine how far they are in space. So this is another feature. Also, they have some, in this case, I'm not showing it here, but they had some kind of measure of how well the key points between two people align. This is another score. So the thing is that you have several scores, several sources of features, but you have to somehow combine them into a single score, right? So then they would define maybe a weighted sum where they would define the weight of every term of the sum manually. And this, I would argue that is not great, because essentially you have to manually set the weight of everything, when ideally with learning methods we would like this to be done automatically.
Okay, thank you.
Okay, so this was a bit of background on specific examples of graph methods and how graph methods and learning have been somehow combined. And now I would like to, this is the last related work that I would like to talk about, and it really doesn't seem so related to what I've been talking about. And I'm just going to talk about it because we somehow also exploit this in our paper, and this will appear later in the talk. So this is a paper by our group, which was presented at ICCB 2019. And here, this model, this is called Tractor. And the idea behind Tractor, it's quite simple. Essentially, Tractor was a bit challenging in the sense that at the time it showed better performance than many graph methods, while being extremely simple in nature. So Tractor actually doesn't even require training on tracking data. So for this method, you just need to train an object detector, such as faster RCNN. And the idea is that what Tractor does is that it's an online method. So the idea is that you have a box in one frame. You start with a set of boxes in one frame. And what you do is that you take these boxes, and at the next frame, you just paste them as they are. So you just, for the next frame, you just initially put the same boxes you have in frame one, then you paste them exactly in the same coordinates in frame two. And then what they do is that for every box, they take the regression head of faster RCNN. So just to recap, in faster RCNN, you have a neural network that given a box will try to refine their coordinates to be tight on the object. So the only thing that Tractor does is that given a set of initially kind of good estimated boxes from the previous frames, it just refines every single one of them to be tighter on the object. And this idea you can apply iteratively across the video. And it turns out that this approach, which is extremely simple, and as I said, you only need an object detector for this. You don't need any tracking graph or anything like that. It works really well. So at the time, this was state of the art by a significant margin. And the idea is that we see this approach as promising because this approach somehow can exploit the low level information. Like this is very good at when there's like little frame movement across frames, it does a very good job of keeping track of objects, but it misses on the kind of long-term relationships where graphs do a much better job. So as I will explain later, we combine this approach with graph formulations. Was the idea of Tractor clear, or?
Yes. But here you refine the coordinates using just that one I had.
Exactly. So in faster RCNN, like quite popular object detector, there's some network that if you give it an image patch, it will give you the refined coordinates
Okay.
of a bounding box that will be tied around that object.
Okay. Okay.
So the idea is that you essentially start at frame here t-1, then for frame t you just use the same coordinates, and then you feed this region of interest to faster RCNN, so to this regression head, and this will tell you, okay, you need to move it a little bit to the right.
Okay, so you just detect, you don't track in the first case. Based on see, that's what I understood. If you keep the coordinates same and you feed it to the model, it says that you have to move to the next patch. Yeah.
Exactly. That's the idea. So you just paste it, and then you just predict a shift in the bounding box coordinates.
Got it.
And that's everything you have to do. Yeah.
Got it.
Okay. So yeah, now moving on to our approach. So like the high level idea of our approach is that we want to have a network that can somehow encode high order information among detections. And instead of relying in this two-step process that I was talking about before, where first you do feature extraction and then you do optimization, we want to do everything at the same time. So we want to have our input sequence and then directly predict the links that will be joining them. And we don't want to, ideally, we don't want to do any expensive optimization, despite accounting for high order information. So I will go into detail later, but the main idea is that we want to put all the focus on learning. So we want to avoid as much as possible having to rely on expensive optimization solvers. Okay, so let's look at the pipeline quickly. Okay, so the idea is that, as I said before, we start with a sequence of RGB frames and object detections for each of them. And the idea is that first we have a CNN here in blue that is shared for all nodes in the graph. And essentially it takes the RGB patch corresponding to every box, and it outputs an initial embedding. So this embedding is somehow a vector representing the appearance of the image. Also, so essentially for every node in the graph, we have this appearance embedding representing each object. And then on the other hand, for every edge in the graph, we essentially take the relative, like we take a simple vector of the relative coordinates of two objects, and we feed this to an MLP, a multi-layer perceptron, and again input an initial embedding for every edge. So the idea is that we have our initial graph, and we have one vector per node and one vector per edge. And the idea is that now we want to somehow combine this information across the graph in order to obtain high order information. So this we do with a message passing network, which is essentially a neural network that operates on the graph, that learns, that allows neighboring nodes to communicate with each other. And the idea is that this outputs the same graph, so the same number of nodes, the same edges, but it updates the embeddings. So after this message passing network, what we have is new node embeddings and new edge embeddings. Okay, so once you have these new node embeddings, what we do is that we apply a classifier on top of every edge. So essentially, for every edge, we apply a binary classification network that outputs a classification score between 0 to 1. And essentially, 1 means that these two objects belong together. In this case, this blue pair, and red, which is most of the edges, means that there's no like that the two objects do not belong to the same trajectory. Okay.
So there is a question regarding graph construction. Maybe you could just explain about graph construction. The question is about how the orientations are picked to form the nodes. Yeah.
Mm-hmm. So in principle, you connect every node. Like, first of all, this graph is undirected. So essentially, it doesn't matter the order of the edge. They are just connected. Like, there's no direction in the edge. And you connect every pair of detections that are in different frames. So the idea is that if, for instance, these three guys, they are in the same frame, they of course cannot be in the same trajectory. So there's no need to connect them. We only connect things that are in different points of time. So this would be like the general case, but what we do in practice, and this I wanted to explain later, but I can already explain, what we do is that we apply some pruning in this initial set of edges. So essentially what we do is that we compare the appearance embeddings, and we just, so given a node, we only connect it to its 15 nearest neighbors regarding appearance. And the idea behind that is that, first of all, if you want to connect everyone with everyone at all the other frames, this is quite expensive. Like the number of edges grows quadratically, more or less. And this can be expensive in terms of memory. But also, if you think about it, you are storing a lot of edges, which are most likely going to be here labeled in red. So you have a lot of edges between nodes that are definitely not going to be in the same trajectory. So this makes your classification problem quite unbalanced. So the idea is to just filter out the edges that we know for sure that will not be active. But
yeah, yeah, please go ahead. Yeah, please finish your thought.
Okay. 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 So this is the high-level pipeline. So you have your input, you construct the graph, you do message passing on top of this graph, and lastly, you just classify every individual edge. This is the high-level pipeline. Now I'll explain every.
Yeah, Anurag has a lot of questions. Anurag, can you just unmute yourself and go ahead? Anurag. Okay, I'll just read out his questions. First question is, are the bounding boxes to be provided during training? Are they provided during training?
If they are, sorry, what?
Bounding boxes, are they provided during training? That is the question.
Exactly, yes, yes. So the data set that we're working with, it is the mod challenge, and you have a set of public detections which every method is supposed to use. So this initial set of boxes, this is given, we don't detect them, and this is our input.
Got it. Yeah, Nikhil, please just go ahead with your question. Nikhil.
Hi, Guillem. I have this question that in this case, the graph outputs are sparse, right? So will that be an issue while training the network? Because the graph networks are very sparse. So do we need to do any additional term for that to balance it out?
Any additional what?
Any additional loss term like that to balance?
So how do you counteract that sparse nature? That is what he's asking you.
I mean, you mean the sparsity? I mean, like having sparse edges, this I think is not problematic. So like graph networks can deal either with dense edges or sparse edges. The problem really lays on the imbalance on the sparsity of here green edges. So there are very few. If you see this example here, you have only 1, 2, 3, 4 edges connecting the same objects in the same trajectory versus a lot of edges that are labeled in red, which means that they are not like the two objects are not in the same trajectory. So essentially, this makes the classification problem very imbalanced. And what we do, we don't do anything too fancy here. We just, so essentially our classification loss is a binary cross entropy. And the only thing that we do is that we have a weight. So for in the loss, you have one weight in the positive term. So like for the positive cases, that kind of gives it more importance in the overall loss. So you have a weight that makes sure that the positive examples are as relevant as the negative ones in the loss. And this this is a very common technique in these unbalanced classification problems. And this ensures that that these few very sparse good edges still play a relevant role in the loss.
Does that answer your question, Nikhil?
Yeah, got it.
Follow up? Okay, Anurag, please go ahead. Anurag.
So, Mr. Brasó, the question that I have is this. So the way the graph is constructed, is it, I mean, I'm going to say the steps that I understand. First, I will break down the entire video into frames. Then for each frame, I will perform some pre-processing to generate the bounding boxes around the objects. So once I have the objects with the bounding boxes, each of these object is a node.
Exactly.
So now I will construct the graph along the time dimension. Nodes within the same frame have to be connected to the nodes of the next frame. Is that how the graph is constructed?
Exactly. Next frame and also future frames. So here, I think I didn't draw all the possible connections, but in practice, we have up to 15 frames per graph. And the nodes that are far apart in time, so frame 1 to frame 15, they will still be connected.
So, but the the doubt that I have is this: how would you know to which node you have to connect in the graph, like in the future?
The thing is that you don't know that in advance, right? Like this is what you want to decide in the end. So at the beginning, you just have all the possible edges. So, I mean, again, with this pruning that we do, but in theory, you could have all the possible connections. And your goal is to actually determine in the end which edges are the ones connecting people in the same trajectory.
And Anurag, just a note that this is for pre-recorded videos. This is not in real time. This is pre-recorded videos.
Sorry. So you're asking me about how I decide the labels, or what do you mean?
He's asking that how we decide the weight of the connections. Like you will use a Gaussian kernel or a...
No, Anurag, just please follow up what exactly you meant.
So what? Since this is a recorded, I mean, I have the entire video. So that's how I already know which nodes will be present in the next frame. Is that so?
Exactly. So exactly, like in this example, for instance, you already have all the frames available. But if this was just real time, you would have just one frame for the current frame, like the last frame you've seen, and then you have the past frames. So you can still have like only two frames and still have this graph formulation. So two frames, but still one node per object detection. Edges go from one frame to the other, and the same idea just applies.
Okay. Does that answer your question, Anurag?
Yes, sir. Thank you. Thank you.
Okay.
So
Was this clear? Okay. Thank you.
Please go ahead.
And any other questions in this regard?
We will interrupt you if there are any in the chat. You please go ahead.
Okay, cool. Okay, so yeah, this was the high-level idea. So graph construction, neural message passing, and in the end, classification. And now I will go into detail into every section of the pipeline. So, okay, the first thing regarding graph construction, as I said, our goal here is to have for every node and for every edge in the graph an initial embedding that represents it. So for nodes, this is quite simple. So you have your initial image patch, you feed this to a CNN. The CNN is shared across the graph. And this CNN, this is already trained. So this CNN, we train it for the task of re-identification. So this CNN is trained so that it outputs an embedding that when you compare it to other people will tell you whether, if you compare them in terms of distance, people who have the same identity should be very close to them, and people who are very different should be far apart regarding this embedding and Euclidean distance. And the idea is that you use this CNN for every node, and you directly output this here in yellow, this node embedding. Now for the edges, we have a vector where essentially one component of the vector is the relative distance for the x coordinate, relative distance for the y coordinate. Also, we have the Euclidean distance between these initial embeddings. So we have the re-ID score, so to say. So this distance telling us how far they are in terms of appearance. And also we have a vector telling us how, a score telling us how far apart they are in time. So what's the time distance between these two object detections? And the idea is that you feed this vector to an MLP. And then you get an initial edge embedding. So this is just to get like an initial representation of pairwise relationships in the graph. Okay. Now the idea is that once we have this node and vector for every edge and node in the graph, we want to combine them across the graph. And the way we do this is with this neural message passing progress or graph network. There are several names for it. They are all more or less the same. And the idea is that you want to iteratively combine information from nodes to its neighbors, to update both the edge embeddings as well as the node embeddings. So how do we do this? The process can be essentially, this is a sequence of steps. We call these message passing steps. And every step is divided into 2 updates. So for every step, first you update the edges and then you update the nodes. So first, for the edge update step, it is quite simple. So the idea is that for every edge, you take the pair of incident node embeddings. So you essentially have 3 vectors. So you have 2 node vectors and 1 vector for the edge. You feed this to an MLP, and then you get an initial, you get the next edge embedding. So essentially, this just means that you combine an edge with its pair of incident neighbors to get an updated representation. So this is quite simple, I hope. And now for the nodes, we have a bit of a problem, because for the nodes, the idea is that if you are a node here and you want to update your features based on those of your neighbors, the number of neighbors you might have, you don't know it in advance. So for instance, one idea would be to, okay, let's take all the vectors from the neighbors, we concatenate them, feed them to an MLP, and get a new embedding. But the idea is that we don't know this number in advance, the number of neighbors. And also, we don't really care about the order of neighbors. So ideally, we would have to have some operation that does not depend on the order. So the idea here is that what you would generally do is take, given a node, all the edge embeddings from the neighbors, because if you recall, these edge embeddings already contain information about the neighbor node. And now you could just take them, and since again we don't know how many of them we have, we need an order invariant operation and an operation that does not depend on the order. So this could be just a sum, for instance. This could be a mean or like an average, sorry, or this could be like a component-wise maximum, essentially some kind of pooling operation that combines all the neighbors into a single vector. And in general, this is how graph networks operate. So you would take the aggregation of all the neighboring edge embeddings. You would add them together, feed them to another network here. This n sub v, feed them to this network, and then get a new node embedding for that node. So this would be like the vanilla node update. But what we actually propose in the paper is to modify this in a very simple way. So the idea is that given a node, we already know in advance that some of its neighbors will be in past frames and some of its other neighbors will be in future frames. So the idea is that instead of just aggregating them all at once, we can already include this kind of temporal information in this aggregation step. And the idea is that instead of aggregating everything together, you split the aggregation into 2 parts. So first, you have the nodes in past frames, you aggregate them together, then you have the nodes in future frames, you aggregate them together. And this way you have somehow a past and a future embedding. You split them and then you combine them in this MLP. So if you think about it, the only thing that we did is going from splitting, so from combining everything together to somehow informing this update step about which nodes are in future frames and which nodes are in past frames.
And how do you determine how advantageous is this?
How what? Sorry, I didn't understand.
So the way you have split it this time, so how do you find out whether, is there any score, or how do you prove that it is better?
Yeah, I will show this later in a table where we compare both aggregations. Okay. And it turns out that this is quite better, at least for tracking.
Okay.
In terms of the main metrics, I will explain this later. Okay, so essentially this is it for the message passing network. So we explained how we combine nodes into edges and then edges into nodes here. And the idea is that you repeat this process several ways. So the first time you do this, you have updated every node and every edge. I mean, initially you just update every edge with its neighbors. But then the next step, you already combine essentially the each node's features with all of those in the neighbors. So the idea is that at the first iteration, you just are informed about your neighbors, but then neighbors of neighbors, then neighbors of neighbors, and the idea is that you iteratively include higher order information in these embedding updates. And this essentially allows you to have some, in the end, you have the same graph, but with some embeddings that now have information about the overall graph structure. Okay. So once you've done that, the last step is to take these last embeddings in the graph and just apply a binary classification network on top of it. And this network just predicts 1 for people in the same trajectory and predicts 0 here in red for people who's in different trajectories. So the idea is to use the output of this message passing to classify and determine which connections are valid in the graph. Okay.
There's one question. Anurag, please go ahead fast. Unmute yourself and go ahead. Okay. He asked, how was the neural message passing implemented as a trainable network?
Well, there's a library for it. Like if you think about it, everything that we're doing here is differentiable because essentially we're just doing forward passes through an MLP and aggregation, like this sum operation. This is everything differentiable. So if you write that down as a computational graph, everything you can run a backward pass through all the operations. But in practice, there's this very nice library, PyTorch Geometric, which I used for this project, which makes implementing these things quite easy actually. And
what is the library name again, Guillem?
It's PyTorch Geometric.
Oh, thank you very much.
In the end, if you check out my code, you can see it there. But yeah, I definitely recommend that library. It makes working with graph really easy.
Okay. Yeah, thank you very much. Please go ahead.
Thank you. So, okay, there's one last thing that I didn't mention about the pipeline, which is that after you run classification on every edge, you might end up with some invalid predictions. So if you think about it, like in this example here, we have, for instance, that imagine that we have this node, and if you follow its trajectory, then goes to this other node. But what could happen is that maybe given a node, you predict more than one edge as being active. And actually, this is problematic because then you don't know like whether the trajectory should follow in this direction or in this other direction. So essentially, this is an infeasible prediction. However, yeah, exactly. So this essentially violates some constraints, and essentially the constraint is essentially that given a node, you can have at most one edge going out of it and one edge going inside of it from the past. So what we do in these cases is that we just take the subset of nodes which are involved in a violated constraint. And then here we run, I mean, the thing is that in the experiments, we see that this typically happens very rarely. So only around 90 of all the constraints, around 99% are satisfied when you just threshold the classification scores. But for a very small subset of them, you might have these violations. So then we just consider the subgraph, so the subset of nodes and edges are involved in these violations. And then here we have either a very simple heuristic. So essentially, in these cases, you just pick the node with the highest classification score. Or you can do this, this is like just a simple heuristic, but you could do this also in an exact way with a linear program. And essentially, you just make sure that in this subgraph, you get rid of all the violations. And essentially what you do now is that you paste that in the original graph. So you just get rid of these edges that were violating the constraints. and you end up with a graph that is feasible to get trajectories from. Okay, so this concludes the explanation of the method itself. I hope it was clear. If you have any questions, I think now would be the moment regarding the method.
Yeah, any questions, please put them in the chat. So yeah, I think we have none for now. Please continue, Guillem.
Okay, perfect. Okay. So now just for some implementation details, I think most of them are already mentioned, but the thing is that now I basically explain the method on a kind of theoretical way, like a high level way. But in order for this to work and in order to make it state of the art and make it work correctly, of course, this also requires some engineering. So some of these engineering decisions are here. So the first thing is that the CNN that we're using, in principle, you could train it all the way. So you could do the forward pass through the CNN, then have the graph network on top, the final classification, and you could train everything jointly, right? But the thing is that this is not really, I mean, first of all, this is very slow. Because if you think about it, like we have some of the graphs are up to 500, have up to 500 nodes, which means that you have a byte size of 500 images in a single graph. And ideally we want to have, like, when we train this network, we want to process several graphs at a time. So this means like maybe batch size 8 means 8 times 500 object detections, around 4,000 images. This is quite expensive in terms of memory. Exactly. And the idea is that we said, okay, like before we train this CNN, let's try to have just the pre-trained features. So you can actually train the CNN for the task of re-identification, which I already explained, just having embeddings for every image that represent how likely it is that the two objects are the same, and then freeze that. And then it turns out that this works very well. And when we actually try to train the CNN all the way, apart from being very slow, didn't really improve that much upon the baseline. So we just decided to just keep the CNN frozen and not train it. Okay, something else, like when we build these graphs, even though we work with object detections at test time, we also train them with the ground truth boxes, essentially the ground truth annotations of the boxes. And we just simulate small displacements in the coordinates, or simulate missing detections. Because we saw that this led to more stable training. What else? Something, again, a design choice that we had here is that when you see videos, like real videos recorded like about like 25 or 30 frames per second, you see that from one frame to the other, there's really not much motion going on. Essentially, objects almost stay the same. So what we decided is that we do not process. Essentially, when we process videos, we only process one of every 5 frames, or like 6 or 9 here. And the idea is that you take the first frame and then you move to the 6th, to the 12th, etc. Because this allows you to capture in a single graph with a given memory budget, you can process much longer sequences. And the idea is that essentially this allows you to cover much longer trajectories. And for the frames that we are not processing, sorry. Please.
Yeah, since we are talking about motion across frames, did you also encounter with the problem of motion blur? If yes, what did you do to deal with it?
Yeah, definitely. So like this, I think it's very common in video data sets. But to be honest, I didn't really approach it in any specific way. Like the thing, like this problem is there, but we don't tackle it directly in any way. You could say somehow we sorry.
Please go ahead.
No, like I mean, this is what I was going now. Like what we do though is that, like for these frames where there's some motion blurring, essentially detections will not be great, especially the public detections. And this is kind of a matter of luck. So when we choose one of, I don't know, out of 6 or out of 9 frames, what could happen is that what could happen is that maybe you get unlucky and then you choose the frame, which is not great. But this is why we have Tractor. Again, this is the paper that I was talking about before. And what we do is that before we create our graphs, we just run Tractor on the detections. So this gives us a much more precise set of bounding boxes, because Tractor is somehow robust against motion blur. And this essentially gives us better boxes that hopefully do not suffer so much from this kind of problems. And also what, okay, thank you. And also what we do is that, okay, since we process one of every 5 frames or something like this, in between, we still have to complete our trajectories, right? So we know that an object is at frame 1, then at frame 5, but what happens in between? So one option is just to interpolate the coordinates in between, do bilinear interpolation, for instance. But what we do is that we also use Tractor for that purpose. So if you know that an object is here and then here, in order to better interpolate their trajectories, we use Tractor to fill these gaps. So the idea is that Tractor is really good at these low-level motions, but graphs are much better at capturing the long-range trajectories. So we kind of get the best of both worlds by using Tractor for the high frame rate and using the graph on the lower frame rate.
Yeah. Thank you. Yeah, please go ahead.
Okay, so now for some results. Sorry, is there a question?
No. Please go ahead. Good.
Okay, so now for some results. The first experiment that we ran was evaluating the number of message passing iterations that we have. So this network, as I said, at the iteration 0, we only have pairwise relationships. And as soon as we move from 1 iteration to 2, then we have this high order relationship, right? So here we are plotting MOTA and IDF1, which are the main tracking metrics. MOTA somehow accounts for how many boxes you have covered in total. And IDF1 accounts for how well your identities match to the ground truth identity. So it's like a measure of identity preservation. And you see, for instance, that IDF1, when you go from 0 to 2 message passing steps, so from no high order information to high order information, you see a massive increase. So from over 5 points, around 5 points of increase in IDF1, and around 2 points of increase in MOTA. So what this is telling us is that this high order information is crucial for identity preservation. And you see that up to 4 message passing steps, this seems to increase, and then somehow it stabilizes. So this tells us that essentially up to a certain point, we still can gather high order information, but up to a certain point, then we don't get any extra information out of that. The other 2 experiments we run for ablation studies are these 2. So in the first one, we essentially, as I said, for edges, we initially have a set of features that we then fit to an MLP before it goes into the message passing network. So what we see is that we said, okay, in these initial edge features, we have the time distance, the spatial distance, and the appearance distance, right? So in principle, the MLP is fusing all the sources of information together. So the question is, okay, what happens if you restrict the access of this information? So for instance, if we just put the time distance, so in principle, the network only knows how similar people is and how far they are apart in time. And we see that still this performs decently, but definitely not great. It's quite far from the best performance. And then we say, okay, sorry.
Can you also elaborate? Can you also elaborate upon MOTA and IDF1? Like the audience, we are not really familiar with these matrices.
Mm-hmm. Okay, so the first thing to say is that evaluating tracking is quite hard. Like in general, these metrics need to account for many things, and this is definitely not straightforward. So this is why MOTA and IDF1 cannot be as easily described as for instance, accuracy or recall or precision. But the general idea here is that MOTA combines the main 3 sources of errors in tracking. So one of them is false positive boxes. So essentially, how many of your output boxes are not an object? Then false negatives, which is the opposite. So after your out of your output boxes, I mean, essentially, how many ground truth boxes you are missing. And the third one is called ID switches. So this means that within your trajectories, you are changing the ID of the underlying identity. So essentially, you have false positives, false negatives, and ID switches. You add these three things, and then you divide it by you normalize it for the number of ground truth objects, and then you get a score. So ideally, like MOTA is 100 whenever you have 0 false positives, 0 false negatives, and 0 identity switches, which is perfect. But then it goes down as you move there. However, MOTA generally it's the main metric for tracking, but people might criticize it because false positives and false negatives depend heavily on the quality of the object detector. I mean, these are object detector errors, right? While ID switches, which is the tracking specific measure, ID switches have like a relatively small role in the overall score. So this is yeah. I mean, essentially, MOTA summarizes your detection quality, which plus the ID switches. Then IDF1 is a bit more hard to describe, but the idea is that you have, on the one hand, you have your trajectories, and on the other hand, you have the ground truth trajectories. So the idea is that you match them somehow, and then essentially you compare how well your overall. I mean, you have some bipartite matching, and the idea is that you compare how well your overall trajectories adjust to the ground truth trajectories. So this accounts for the entire trajectory. So this is more of a measure of how well you link boxes. It's a bit technical. I mean, the thing to keep in mind, and at least that's how I do it myself, is that okay, MOTA accounts for how many boxes you have covered and how good is the quality of your boxes. And then IDF1 accounts more for how well you are linking these boxes. And then here, I haven't explained these metrics, but here, MT means mostly tracked. So how many trajectories you have almost completely covered. This is mostly lost. How many trajectories you have mostly lost. False positives, false negatives, and these ID switches. But essentially, the things to keep in mind are MOTA and IDF1, which are the most representative metrics. Yeah. Was any questions regarding the metrics?
No. Yeah, you answered them. Please go ahead.
Okay, cool. So regarding, so here I was talking about which sources of information we give our network access to. And essentially, you see here that when you, essentially having position features, so allowing the network to compare the relative position of different objects makes the biggest difference here. So you see that IDF1 goes from 52 to 68, which is already state of the art. So you see that essentially this position information is very important for the network. And lastly, you get the last improvement. You get it via adding the VIT score in the edge features, which gives you the last boost. Okay, so this was for sources of information, and now we did an ablation study on the network architecture. So this is what I was being asked before. Regarding whether how we measure how these different aggregation steps that we propose. So if you recall, for the node update step, we compare either aggregating all neighbors together versus splitting the aggregation into future and past. And again, we see here essentially an increase of here. The vanilla is the first one, time aware is our proposed method. And you see an increase, and essentially every single metric improves. And it's especially remarkable. Here we include one last column, which is constraint satisfaction rate. So this means out of these constraints that I was talking about in the rounding step, with these infeasibility constraints, this is the percentage of constraints that is automatically satisfied just by thresholding a classification score. So like essentially how many situations you find in which you have these violations, in which one node has, for instance, 2 edges out of them. And you see that this time-aware step helps a lot in this regard. So the vanilla one only has around 82% of constraints satisfied, and the time-aware one has almost 99%. So this essentially means that the results of this network are almost automatically feasible. Okay. Now coming to an end, just some benchmark results. So all of this was done on validation results. Now, when we submit to the tested server of the mod challenge, which is the main, sorry, which is the main data set for object tracking, we submit to 3 data sets, the mod 15, mod 16, mod 17. And essentially we come up at the top of the 3 of them among published methods. So here we have Tractor, which is, as I said, we use Tractor, which is previously state of the art. And we improve here up to 5 points, in terms of IDF1 up to 11 points. Here, yeah, again, 7 points, 6 points. So we see that Tractor, which at the time was state of the art, we again exploited, but surpassed it by very significant margins. And you see that margins, our improvements are most significant in terms of IDF1, which kind of supports our story that this graph allows you to keep identities very well. So you see that we are quite far in terms of IDF1 from all previous methods. And also here you see that in terms of here errors this is measured in frames per second. You see that we are also quite competitive in terms of speed. So we're not only better, but also faster than most methods. You see that our method runs at 6.5 frames per second, while other graph methods, here we have a G for them, sometimes they go up to 0.6 frames per second, or like 0.1, 0.5, 0.8, so around 1 order of magnitude slower than us. So overall, this is due to our sparse frame processing speed and essentially the lack of the lack of a need for relying on optimization solvers. Since we have only this rounding step, which is very fast, our method is overall quite fast. Okay, now let's look at some qualitative results. So you see in general, these occlusion cases, these are the most challenging ones. And you see that our method handles these situations quite well.
Sorry, Guillem, how do you define occlusion? Sorry, I'm not familiar with it.
Sorry, occlusion, by occlusion, I mean that there's 2 people who are like one of the persons is blocking the other one. So someone is not fully visible, for instance.
Got it.
In this case, for instance, lots of occlusions in that sense, a lot of people being covered. Yeah, then for this sequence, which is quite challenging because there's lots of people and in general quite a bit of occlusions here, for instance, in this left side, you see that the method still manages quite well to preserve identities. Again, this is not perfect. You can see some flickering here, for instance, some ID switches. But overall, I would say it worked quite well. Also, this is the mod challenge. Some sequences are there's like strong movement, strong camera motion. These are quite challenging, but you can see how, yeah, again, some mistakes, but overall decent performance.
Very, very good. Very impressive.
Thank you.
This is extremely hard as well, like a very active research area.
Definitely, yeah. So like tracking actually now I think it's getting more attention, but it's actually a quite challenging problem that has not got that much attention, at least in terms of deep learning. Up until now, it has not been fully exploited. And as I said, up until 1-2 years ago, state-of-the-art methods were still heavily relying on classical optimization, handcrafted stuff. So I think it's quite exciting to really see deep learning making a nice appearance here, just as it has done in object detection or other tasks.
Good.
So yeah, this is it from my side. if you, yeah, so you can check out the code. The code is available, and I will be updating it next week, hopefully with some new results. So
Yeah.
yeah,
So
you
we
guys
have,
can check it out. You can reach me at any time, and yeah, thanks a lot for having me.
so we have few questions. Nikhil, please unmute yourself and go ahead fast.
Hi Guillem, I have this question. Like,
Mhm.
what is the intuition to use the neural message passing network? Because the prior work did not use it. Like, what motivated you to use that?
Exactly. Yeah, good question. So this I was trying to motivate it a bit at the beginning. So in general, you would only instead of using a graph network, we would just use like probably a Siamese network in which you would consider only a pair of object detections. And the idea here is that the graph network can encode not only pairs of like the relationship between pairs of object detections, but also between more than one pair at a time. So higher order information. So this means that, for instance, if you want to know if two people belong to the same trajectory, you probably not only want to look at these two people, but you also want to look at all the other options you had. So all the other candidates, and then have a network that somehow operates on all of them and outputs a score that accounts for all the possibilities. So this is the kind of intuition behind why higher order information is useful. The intuition is that you want to compare not only pairs, but also like a higher number of possibilities, so to say. And a graph network implicitly does that by operating on the whole graph.
Yeah. Does that answer your question, Nikhil?
Guillem, like the way you defined the graph network, it motivated you to go with the neural message passing network. The way you are defined the graph network has motivated you to go for neural passing.
Yeah, like the thing is that this graph, I don't define myself. This has been around for quite a few years. And the only thing that I did is like, I take this graph formulation of multiple object tracking, which again is well established. And I combine it with this graph network. And if you think about it, it's quite natural, right? You have a graph domain, you have a graph problem. So the right tool to tackle it is probably a graph neural network, right?
Okay, got it. Thanks.
Mm-hmm.
Anurag, please go ahead. Yeah.
Yeah. So I have a question. What comes to your mind as a future problem that can be tackled from this particular perspective, the perspective from your paper?
Mm-hmm. Okay, yeah, really good question. So you see, like from the beginning, I've been assuming that that object detections were given, right? And actually, object detection is very important for multiple object tracking. So I mean, essentially, your tracking results cannot be so good unless your detections are good enough, right? So one thing helps the other one. So one natural thing to ask is whether we can also tackle again with graph networks both tracking and object detection. So you could try to tackle the two problems together. Then this would be something like joint tracking and detection. There's already some work going on with that, and I'm personally working on that too. Then you can also think about what happens about long range connections. Like now with this graph network, we are only processing up to 15 frames, for instance. Can we go much bigger than that? Can you actually process long range connections? Things like this. This would be another direction.
Yeah. Does that answer your question, Anurag?
Yes. As a follow-up, I also want to ask, how difficult would it be to take it to like streaming live video? Because in
Like
that case, the graph construction would be very difficult.
Real-time object detection, yeah.
Mm-hmm. So yeah, I think in principle, I haven't tried it. It's something that's kind of in my to-do list. But in principle, it shouldn't be that hard. Like I don't think, I mean, in order for this to be real time, we would probably just need a lightweight CNN, but this should be fine. And the only thing we should do is essentially that now we are working with like a large set of frames, but if you want to have it in real time, then you only can consider one frame, so you cannot look into the future. So this would be essentially just looking at the current frame and the past frame and do this with like short sequences, so to say. But this, at least in theory, shouldn't be too hard to do.
So, but we do not have the ground truth bounding boxes, right, for real-time videos?
No, but I mean, I mean, you only need ground truth to train the network, but once the network is trained, you no longer need ground truth.
But the network, we are passing the bounding box information as well, right?
Exactly, but I mean, the bounding box, you got it from an object detector, right?
Pre-trained object detector.
Exactly.
Okay, thank you, Guillem. I have one last question. I'll just share my screen. I have a question in the tractor paper.
Sure.
Yeah, so here you are, how do these, can you comment on this extension if possible? We're going a little off topic, but I just
Definitely, yes. So yeah, tractor essentially has two main issues. The first one is that this kind of strategy that essentially you go from frame to frame and you just paste the boxes and you refine them. This works well if the frame per second rate is fast and there's not a lot of camera motion. So essentially, this means that when you paste the box from one frame to the other, in order for this refinement step to work, your initial box needs to be quite close to the final box, right? But this cannot happen if there's like a lot of camera motion. So here, what they do, this CMC is just camera motion compensation. So what they do is that they estimate this motion, and then according to this motion, they put the box in the right place. So in order to have like a better estimate. Then this is one issue, like essentially dealing with this large camera motion. Then second issue that they have is that essentially, I didn't go into detail in that part, but essentially they kill trajectories as long as they overlap or they have like a bad object detection score. Like essentially you keep doing this process until you are overlapping with someone else or you have like a low objectness score. And what this means is that you will have a lot of ID switches because you kind of are going to have like a lot of short trajectories that you will not be able to recover. So you will just give next different ID to every next trajectory. So what they do is that they use this re-ID head, which essentially means that when you start a new trajectory, instead of saying, okay, this is a completely new person, you look at all your past trajectories and look at this re-ID score to say, okay, like this guy looks very similar to this other guy in the past. So then I'm gonna give it the same ID. So I'm just gonna say that they are the same person. So what this means is that you're gonna have less ID switches.
Very good, great work, Guillem, from your lab. Very good. Thank you for the excellent presentation. Thank you for your time. We greatly appreciate it because this paper is really for like I'm not familiar with this graph area, but you really explained it very well. It's
thanks,
really
Guillem. Thanks for taking time and giving presentation.
Okay, I'm really glad to hear that. Thanks a lot, guys. I think you had really good questions, and I appreciate a lot you inviting me here.
Let you go. Thank you for your time. Thank you very much.
Okay, great. Thanks a lot.
Yeah, have a nice. Bye.
Okay, bye.
Bye.